CGB, and Cx equal to C pi over here, and here Cx equal to CSB plus CGS. Okay, so therefore we have only two nodes in the circuit. If there are two nodes, two capacitors, effective capacitors in the circuit, although physically you may seem to have more number of capacitors, but eventually they boil down to only two capacitors in the circuit, and therefore there will be two poles. Now, the pole associated with node X, we can call that as omega P1 or omega Px, and that is equal to 1 over Rs parallel 1 over Gm times Cx, and omega P2 equal to omega Py equal to 1 over RL Cy. Okay. Now this is so at X, the equivalent resistance looking into X is 1 over Gm this way and Rs over this way, and they are in parallel, so that's a Rs parallel 1 over Gm, and here it is also going to be the same thing. And omega Y is resistance looking into the output node, which is RC here because we have considered RO equal to infinity. Here it is RY, at this node it is RD because again RO equal to infinity. Okay. Now, if I do not consider RO equal to infinity, that means let us say there is a finite resistance RO over here. RO over here. If that happens, now keep in mind RO is a resistor connected between two nodes X and Y. Can I apply Miller effect here? I just mentioned in the previous one that I cannot apply Miller effect. Now I would expect you guys to give me an answer why we should not apply Miller effect to RO. Okay, and solve it, find out the equivalent resistance. So that will be part of the assignment. Why RO should not be converted using Miller effect. Okay, this is what I am expecting you to answer. Now, the next thing that I also want to say is that in this case, now yesterday we talked about something called a dominant pole. Dominant pole is the high frequency pole which has a magnitude which has the lowest value. For example, the high omega P1 and omega P2 are the high frequency poles. So therefore, the whichever is the smallest of these two will become the dominant pole. In this case, if you look at it, RS parallel 1 over Gm would be roughly equal to 1 over Gm. Okay, if that is the case, isn't omega P1 roughly equal to Ft of the transistor? Ft is the unity current gain frequency. Ft is the unity current gain frequency. So therefore, omega P1 is a very high frequency pole, which imply what it means is that omega P2 is the dominant pole in common base / common gate topology. Okay. So this wraps up the common gate, common base amplifier topology. Any questions on this? So, so there is a question which is there are a couple of questions now. Now let's see. Is Cx and Cy nearly equal? Now Cx and Cy, will they be equal? Need not be, right? Why should they be equal? Unless you try to equalize by adjusting the load capacitance, but load capacitance is not always under your control. Okay. Now, how does omega P1 being Ft imply omega P2 being a dominant pole? Uh, now, okay. Now, if you look at it, omega P1 is roughly equal to Ft. Ft is the highest frequency that the transistor can operate at. Okay. That means there cannot be any other pole greater, any other frequency that the transistor can give you any meaningful information. Okay, above that. Okay, that means if omega p2 has to be greater than ft, that means omega p2 is giving us some additional information, and that violates the principle that ft is the highest frequency at which the transistor will operate. So that means ft is the maximum frequency that a transistor can operate. So therefore, omega p2 has to be the dominant pole because it is a value less than omega p1. Does it answer your question? Okay, I assume that it answered your question. The audio quality, I just want to ask one of you can answer over the chat. The audio quality in the recording that was uploaded, it looked okay to me, but I did not listen to the whole lecture. So, was it also intermittent, just like the network connection, or it was smooth? Somebody asked if Cx is much larger than Cy, then omega P1 will be smaller, right? Cx is much larger than Cl. That is what I said, right? Cy. That won't happen because Cy has a load capacitance, and load capacitance is much bigger than usually the any other capacitance that is there in the intrinsic capacitance that is there. Because there will be always load capacitance will have some external capacitance. Yes. Yeah, you're right. Okay. So now let me proceed further. Okay. So high frequency response of the follower. So I'll draw the emitter follower circuit first. So that's the emitter follower, and then the source follower. So now again, both the circuits, as far as the high frequency components are concerned, look identical, except that in case of source follower, we have this additional CSB term which is absent here. Keep in mind that the CCS and CDB, both terminals are connected to AC ground. In fact, one of the terminals is connected to DC ground, and the other terminal is connected to power supply, which is also an AC ground. So therefore, these capacitors are as good as non-existent. They're physically there, but they are electrically absent. Okay. Now, in order to solve this, okay, here if we look carefully, we have a floating capacitor C pi between node A and B, and CGS between node A and B. We could apply Miller effect in this scenario, but I would choose to apply draw the small signal model and analyze this, because till now I have been solving both the topologies using associating a pole with each node. But here I would deviate from that a little bit and draw the small signal model and solve the obtain the poles. And in fact, since we are drawing the small signal model, we will see that we are in fact getting the zero also of the frequency zero of the frequency response. So the unified model, small signal model, is going to be like this. So I know actually what I'll do is I'll do it for the BJT case, and then you can do it for the MOSFET also. The similar thing will hold. Okay, and here is the Vin. This is node A, and this is the node B is the emitter. This is the node B of the amplifier. B of the amplifier. Okay. So this is the small signal model, and here the similar model will hold also for the MOSFET case, where we'll have, instead of C pi we'll have CGS, and instead of C mu we'll have CGB. So I'll do it here. This will become CGB. This, sorry, somehow the OneNote application closed. Okay. Okay, for a MOSFET case, C mu will be CGD, and C pi will be CGS here if we do, and this R pi will become infinity over here. Everything else stays the same, and CL will be equal to CL plus CSB in case of MOSFET. Everything else stays the same. Okay. So now, in order to solve this, we'll apply KCL at node. We'll apply KCL at node A, and applying that we get V out plus V pi by R pi plus V pi S C pi equal to 0. We apply KCL at node B, V pi by R pi plus V pi S C pi plus equal to SCL. And from this, from the second expression, we get, therefore, by solving these two, we get solving the above two equations, solving the above two equations, we get V out over V in Laplace domain as 1 plus C pi over Gm times S divided by if where A equal to Rs by Gm, C mu C pi and B equal to plus 1 plus Rs over R pi Cl by Gm. So, so So I have written the answer, but I will pause for some time and I want you to solve these two and obtain the same expression. So I'll wait for 5 minutes, and when one of you has already solved it, I'll move on to the next one. Okay, so I'm pausing the recording and I'm waiting for you to solve these two equations and obtain this expression. Okay. Did you guys get this by solving these two? Okay. Anyone got it? Yes. Did you guys get it? So yeah, but is it matching up with what I had written here? Somebody said the numerator and denominator are coming of the same degree, but are you getting the coefficients as these? Okay. So some of you have done it. So let me proceed further. Where so from this expression, which is this expression, what you see is that when I do the exact analysis by drawing the small signal model, I not only get the transfer function with the poles, but also we get the zero, and the zero of this transfer function, omega zero, is close to Gm over C pi, which is roughly equal to the Fe. Okay, so the zero of this transfer function is at close to the unity gain frequency of the transistor. Okay, for the source follower, you can set R pi equal to infinity, and you will get the term. If you set R pi equal to infinity for source follower or source follower, set R phi equal to infinity, and therefore you will get V out over Vn of S equal to 1 Gs over Gm times S divided by as squared plus ps plus 1, where a equal to rs over gm, which is similar to that, and then here you'll have the product cgt, cgs, csb plus cl plus cgs, csb plus cl, and b is equal to rscgt plus cgt plus csb plus cl over g. Okay, so this will be the overall frequency response. Okay, and this kind of wraps up the frequency response of all the amplifier topologies that you have studied. Now keep in mind that for the differential amplifier, for the you will have frequency response. So I will just frequency response, or I will say high frequency response of differential amplifier Okay, so in this case, differential amplifier, I'm doing the MOSFET case here. Okay, so V in P, V in N, so it is going to be V out N and V out P. Now in this case, you will have to annotate all the capacitors, the intrinsic capacitors of the transistor wherever they are, but we'll have the frequency response for differential mode, and frequency response for common mode. Okay. Now for differential mode, you analyze the circuit using the concept of half circuit. What it means is that this node P is considered as the virtual ground node, and therefore once you apply the concept of half circuit, this transistor, this configuration would boil down to either, in this case it boils down to the common source amplifier, so you can use the same expression for the transfer function with common source amplifier. Now if I have, let's say, a resistor over here, then this boils down to a common source with resistor degeneration. You apply the frequency response of the common source with common source with emitter degeneration frequency response. Okay, although I have not discussed the common source with emitter degeneration or common emitter with emitter degeneration frequency response, high frequency response, because I will give that as an assignment which we will be submitting on Sunday. Okay, now for common mode part of the circuitry, okay, so differential mode is analyzed by using the concept of half circuit, and the circuit therefore boils down to either a common source or common source with emitter degeneration. So that means concept of half circuit, resulting in the circuit boils down to either common source or common source with source degeneration. Okay. Okay. So whatever I am writing, somebody is saying that there is a big lag. So they want to see the previous slide. So here it goes. The previous slide. Let me know if this is okay. Should I hold on? Is that okay? Okay. And then the next thing is that somebody said the thing that I'm writing is lagging behind. So let me go back to the next one. So here I'm talking about the high frequency response of differential amplifiers. And the reason I'm not discussing it is because the high frequency response of the differential amplifier, let's say we take the differential amplifier in case of a MOSFET, you can have the scenario where it is like this. Okay. And when I'm drawing the high frequency response, I have to get the high frequency response of the differential mode of the circuit, and we have to get the high frequency response of the common mode of the circuit. Okay. So when we are doing the differential mode analysis high frequency response, we already know that we are going to use the concept of half circuit. Okay. Once we apply the concept of half circuit, this circuit translates to a common source amplifier. Now, in case there is some other element, there is a resistor here, then this translates to a common source with source degeneration. Same thing with the BJT base. So therefore, we need not discuss the high frequency response of the differential amplifier because it is similar to the high frequency response of the common source amplifier in differential mode case. Now, in case of common mode, we have discussed in case of common mode, what we say is that if this is an ideal current source, then the common mode circuit, this is an open circuit over here. So if both the inputs move up and down together, the output is not going to change because this won't change, the current change would not be allowed. Now, in order to analyze the common mode circuit, we assume an output is output resistance RSS of the current source. If that happens, then this common mode circuit, equivalent circuit for high frequency response would boil down to something like this: RB by 2 and 2 transistors in parallel. Because common mode means both inputs are moving up and down together, and then there will be RSS over here. So again, the common mode equivalent circuit also boils down to, so this is nothing, this circuit, if I redraw it, it is going to be a circuit which has RD by 2 as the load resistance, and the GM of this is twice GM of the GM of each device, so it will become twice GM, and this will be a source degeneration. Source degeneration resistance is RSS. Now you annotate all the capacitors in this circuit. So the common mode frequency response would behave like a common source with source degeneration. Okay. So in order to, now what I will do is in the homework, I'll give a homework problem on common source with source degeneration or common emitter degeneration, and I will tell you to analyze the differential amplifier, common mode and differential mode frequency response by using this method that I just discussed right now. Any questions so far? So let's take up some questions because this wraps up the frequency response part of the syllabus. Okay, because now I would like to move on to feedback, concept of feedback, negative feedback. Okay, and that is a pretty long and intensive section. So if there are no questions, so I will stop this recording because somebody said please scroll down once. So I am already down. Yes. What is this? Could you show the derivation of the low frequency response of BJT while considering only CS? While considering only CS. So I have to go through the full derivation of the with the CS, low frequency response. Border plot, I will discuss it not today. When I am discussing the frequency, phase margin, gain margin, that's when that is more important because that will be more relevant because we'll be using that concept. So let me go back to page one that somebody has asked. Yes. Oh, so that was given as a homework. So you want me to solve it? Oh, okay. So let me give you the results of that. Okay. For the BJT based amplifier, okay, good point. So let me, since I gave you as a homework, let me give you the poles and zeros of this, and therefore you can pole zeros and the midband gain, and therefore you have the transfer function. Okay. So let me go back to for the low frequency response of the BJT amplifier. For low frequency response of BJT amplifier, we have midband gain equal to the only difference is that R pi comes in parallel, and the first pole due to the coupling capacitor is given by CC1, R1 parallel, R2 parallel, R pi, omega PL2 due to the emitter regeneration capacitance C is roughly equal to 1 plus GMRE divided by CE RE. Okay. So the omega PL3 due to CC2 equal to 1 over CC2 RC plus RL. Omega ZL1 equal to 0. This is due to CC1. Omega ZL2 is equal to 1 over CERE. Omega ZL3 equal to 0. This is due to CC2. This wraps up this. These are all the from this you can therefore obtain the transfer function for each of the cases and the overall transfer function. Okay, now somebody is asking, can you show the page from top once? This page, right? Okay, so let me, okay. Omega PL2 I do not have the exact expression in front of me. Um, so unless I solve it myself, I do not know. But after um, so I'm trying to see where is that. I have to. Um, Okay, so then I have to solve it again. So I think if you follow the same method that we did for this for the MOSFET case, won't you arrive at this thing? I have to derive it myself. I cannot just right away answer it what assumption I made. Possibly. RO equal to infinity. That's a valid assumption to take for this case. Yes, and I have taken RO equal to infinity for all the analysis here also, right? In the common in the MOSFET analysis. Yeah, I have taken that also. In the MOSFET analysis also, I have taken RO equal to infinity. GM is always much greater than 1 over R pi. That's always the case. Okay. Are there any other questions? Okay. If not, I'll stop this recording for now because this finishes up the frequency response. So I will stop it. And let me why don't I do this? Let me then start the feedback on. We have the class on Wednesday, right? Wednesday or